welcome to this video. Today we are going to be looking at sets. This video was made with 11th grade ISC math in mind, but it is pretty useful even otherwise. So let's jump right in. First, let's define sets. Sets are a well-defined collection of objects. When we say well-defined, it means that we should easily be able to tell if a certain element belongs in the set or not. Or basically, there should be no gray area. For example, the set of all colors is a set, but the set of all good movies would probably not be a set. We call the objects in a set elements. A set can contain numbers, letters, words, or anything, but today we will mostly be looking at numbers. It's a good time to familiarize ourselves with the Greek letter epsilon, which is used as a symbol for belongs to. In this example here, the element lowercase a belongs to the set uppercase a. And we use the crossed out epsilon as a symbol for does not belong to. Next, here are some ways to represent sets. First, we can state them in words, for example, multiples of 3 less than 10. Next is the roster or tabulation form in which we list out all the elements as we have done here. Pay attention to the curly brackets, which is how we always represent sets. Finally, the form which we will be using the most is the set builder or rule form, in which we generalize requirements for elements to meet to belong in the set. Or basically, what's the rule the element has to follow to be a part of the set. Again, we have our curly brackets, and how we can read this form is the set contains all elements x such that the colon over here means such that, you can also use a vertical line, such that x is equal to 3n, where n and x are natural numbers, or in short, x is a multiple of 3 and x is also less than 10. The fancy capital N which you see represents the set of natural numbers, which we will look at in a bit. Two important properties of sets are, first, there are no repeats. Basically, the same element can't show up more than once in a set. Secondly, the elements are unordered, or their order doesn't really matter. Here's a practice problem. Pause the video and come back when you have solved it or try to solve it. Okay, and we're back. Roster form was simply just listing out the elements, and the set builder form is as shown here. Here I would like to recommend two things. First, specifically for sets, practice the set builder form a bit, get familiar with generalizing stuff, and also that way you will be able to read and decipher it quickly. Second, more generically, whenever we have practice problems, always pause the video and try to attempt them before we go over the solutions together, because that's active learning, which is probably a lot more useful than just listening to me talk. Here are some types of sets. It might be sort of theory heavy, but honestly, the name of the set sort of tells you everything about it that you need to know. A finite set has a finite number of elements, but an infinite set would have an infinite number of elements. There are examples in green for each type of set. Check them out. The empty set would have no elements. There is only one empty set, and we either show it with the Greek letter phi or curly brackets with nothing inside. The sets underlined in red over here, that's curly brackets with 0 in it and curly brackets with phi in it, are not empty sets because they contain elements. A singleton set has one element, and equal sets are two sets with the exact same elements, but the order of the elements doesn't matter, as we can see from the example. Equivalent sets are two sets with the same number of elements, but the elements don't have to be the same. Don't confuse equivalent with equal. Overlapping sets have at least one element in common, while disjoint sets have no overlap. There are some sets of numbers we will commonly use, and as you can see, we have these fancy uppercase letters which represent them. We have natural numbers, whole numbers, and integers as shown. Rational numbers are basically numbers which can be written in the form a over b, where b is not equal to 0, and irrational numbers, which are shown with that fancy cube with the horizontal line over it, and rational numbers together make real numbers, and real numbers is the fancy r. And then we also have imaginary numbers, which are the square roots of negative numbers, and so on. Finally, we have intervals. If we pick any two numbers, there are infinitely many numbers in between, and we can represent them with intervals. So the two numbers we pick can make up the boundaries. For example, 3 and 5 here. If we include both the boundaries, it is a closed interval, and we use square brackets. So basically, when you see the 3 comma 5 with square brackets on either side, we're basically talking about all the numbers between 3 and 5, which, my bad, does not, which includes 3 and 5. And if we exclude both the boundaries, it's an open interval and we use round brackets. So that would be all the numbers between 3 and 5, but we are not counting 3 and 5. And if we include only one boundary, the interval is half open. And if one of our boundaries are infinity or negative infinity, that side should always have an open interval as a convention because you can't really include infinity. Here's a practice problem. Pause the video for a minute and come back once you've tried it. And we're back. Here's the answer. Now we know about the kinds of sets, so let's move on to the next concept. Okay, so subsets. To define subsets, think of two sets A and B. If each element of A is in B, A is a subset of B, and we have that symbol which we use, which is kind of like a curved less than or equal to. If we go with the Verdi definition, technically each set is a subset of itself. So we introduce another symbol that is proper subset of. It's kind of like less than and less than or equal to. If we stick with our examples A and B here, if A is a subset of B, we can also say that B is a superset of A. Another important thing to note is that the empty set is the subset of all sets. So when we count the number of subsets in a set, these two yellow things over here, each set is a subset of itself and empty set is a subset of all sets. It's important to keep those in mind. These are some properties of subsets below. The ones, if A is a subset of B and B is a subset of C, then A is a subset of C. And if A is a subset of B and B is a subset of A is equal to B. But I would like you not to waste too much energy memorizing these because they are fairly intuitive, and instead just focus on understanding the concept. So for a set with n elements, we would have 2 to the n subsets. Yeah. So let's try an example. We have a set A with 3 elements, and let's find all the subsets. According to our formula, we should have 2 to the 3, which is 8. And we also need to keep the empty set and the set A in mind. So A, B, C, and then we have 2 elements. And finally, we should add the set itself. And if we count them, they are indeed 8. Yep. So if you do forget the formula during the exam, do not panic because you can derive it by testing out sets with 1, 2, and 3 elements as long as you count carefully. So the sets of numbers that we discussed, the ones with the fancy uppercase letters, and our interesting fact over here, kind of fit into each other if you want to apply the subsets concept. Take a look at it. Earlier we discussed that a set can have anything for elements. Turns out it can even contain other sets. This over here is basically a set of sets. But when someone asks you to list the elements, you have to remember that the elements are sets. Each of the underlined things over here is an element, so that means you have to include the curly bracket. If you tell me that just the number 1 is an element of set S, that would be wrong. The element is actually the set containing 1. It is important to be careful there. And then a power set for any set is the set of all subsets of that set. Earlier we had kind of listed all the subsets of a set, right? For a power set, we would put all of those into a set with curly brackets. Let's try an example. Okay, so let's have another set with 3 elements. And the power set would be a set containing all the 8 subsets of A. So we open with a curly bracket. Remember to include the empty set, of course. And the set itself. And there we go. So an interesting bonus question down at the bottom, if you're up to it, is finding the power set of the empty set. This one is a really good test of your concepts. And comment the answer down below if you do try it. A universal set is kind of like a big set from which we can pick elements to form sets for a particular discussion. The universal set kind of depends on the context. For example, if we're picking up letters to make sets which form words, our universe or universal set would be the set of all the letters. We use these symbols to denote the universal set, the ones at the top, the fancy U, capital E, or fancy thing, which I clearly can't draw. I'm going to be using the first one, that kind of fancy U, and your textbooks might use a capital U as a convention. Here we have a few examples of universal sets. So for the set of all squares, the set of rectangles would be a good universal set, and for the set of all rectangles, the set of all parallelograms would be a good universal set. And that isn't to say those are the only correct answers. For either of these, if you set the set of all polygons or the set of all 2D shapes, that would be a good universal set as well. The next one is my favorite concept for sets, which is Venn diagrams. You have probably used them to make comparisons before. In terms of sets, anything which is inside that circle with A belongs to the set A, and anything in the circle B belongs to B. Whatever is in the overlapping part belongs to both. Things which are right on the boundaries don't count as belonging to the sets. The universal set U over here is shown with a big rectangle, and you can draw all your other sets inside it. Here we just have some examples of types of sets as they would look in a Venn diagram. I really like Venn diagrams because they make everything really visual and intuitive. Next we have operations on sets. First we have the union of sets, which represents anything which belongs to at least one of the sets. So next to union, if you see that little symbol between A and B, it's called a cup, and I've shaded A union B in the Venn diagram for a visual idea. Next is the intersection of sets, which is elements common to both the sets. Here we use a cap, which is kind of like an upside down U. If you get confused between the symbols of union and intersection, I like to think of U for union because the symbol kind of looks like a U. And of course we can have unions, intersections, and so on for more than two sets, but I've just shown two sets here, A and B as an example. Then we have difference. A minus B would be the elements in A which are not in B, and B minus A is the opposite, that is elements in B which are not in A. And as you can see, these two are not the same. Then we have symmetric difference, which is the union of A minus B and B minus A. In English, that is elements which belong to only one of the sets and not both. And finally, we have the complement, which is everything in the universe which is not in the set. And there are many different symbols for the complement, as you can see. Any of them are fine. And here are some properties. These are fairly intuitive, but try drawing them out on Venn diagrams because that will really help you get the concept and you won't have to memorize them. A lot of them make sense immediately on drawing the diagrams. Some of them are a bit more trippy, like the last two, and you might kind of have to wrestle with the logic, but they do make sense. I'll just give you a minute to look at them. Okay, moving on. These are De Morgan's laws. Normally I won't encourage you to memorize stuff where it's not necessary, but I would say learn these ones. A silly little trick I used to remember is if you look at the first De Morgan's law, we have A union B in parentheses, and then we have the complement sign. So I kind of like to apply that to each symbol. So we would get A complement, and then the union sign would kind of flip over and become an intersection, and we would get B complement, and you can use the same logic for the second one too. Okay, here is a practice problem. Pause the video and try it. Okay, we're back. So we want the intersection of A naught and C naught, or what is common between these two. So we can kind of use De Morgan's laws over here to kind of simplify this whole thing, right? We take out the complement sign and put everything in parentheses. So now, yeah, De Morgan's law. Yeah, everything we have is A union C, and we want everything which is not that. So because A and C are disjoint sets here, A union C would just be A and C, the separate circles, and we shade in everything except those circles. Yep, that's everything except for A and C. Okay, so we have another practice problem, and pause the video for a minute and try it out. Okay, and we're back. And so the B intersection C is in brackets. So just give me a minute. Yeah, B intersection C is in brackets, so we want to work with that first. Let's shade it in. And we also want everything in A that we haven't already counted, so let's fill that in too. Yep. Okay, so here is another practice problem. Pause the video for a minute and try it out. This one's kind of the opposite of the first two. So we're back. And we've been given this whole part shaded in yellow. And let's look at the part which is actually not shaded first. Yep, I'm just going to shade that in purple. So this is basically this whole part is A union B union C, and we want to, and the actual shaded area is everything which is not that, right? The yellow area, and so that's why we put the complement, and this is our answer. So for these Venn diagram questions, each person might have a different approach, and there is no correct one way to kind of approach the problem. Sorry, no one correct way. But do be careful to avoid mistakes and practice these kinds of problems, because you might get them. So our final concept for today, but a very important one, is cardinal number. That is basically the number of elements in a set, and we are going to do a lot of calculations with these. So the lowercase n and then brackets containing the set is a formal notation for the cardinal number. Now we look at two formulae. So the first one gives you the number of elements in the union of A and B. So you can look at the diagram. It makes things a little more intuitive. So we would count everything that is in A, that is in the Venn diagram, the parts shaded in yellow, and then we'd count everything in B, which is the part shaded in purple. But as you can see in the overlapping part, you can see two different colors, right? Because that and the number of A intersection B is counted twice, and we want to count it only once, otherwise we're overcounting, so we subtract that once, and that's how we get this formula. Pretty intuitive, right? So let's look at the next one. Okay, so this one's a bit longer, but don't be scared. If we have three sets and we want to find the number of elements in the union, that is basically the total. Um, we need to count everything in all three sets. But if you look at the diagram, you can probably see some mixing of colors. There's double counting, and then in one section we kind of triple count. Um, so the places where you see two colors, if we subtract those parts once, those are single counted, but the part in the center, which is the intersection of A, B, and C, gets completely erased. So in the formula, at the end, we kind of add that back. I know these words might sound kind of confusing, so if you want to convince yourself, um, try drawing this out and erasing it. It's kind of hard to like erase only one color on the whiteboard over here, but yep. And if you feel comfortable that way, then learn the formula. We're going to be doing loads of word problems with it, so with practice you'll probably end up memorizing it anyway. So here's our first practice problem for this concept. Take a minute to try, and we'll be right back. Okay, so they've sort of given us everything really clearly, but let's try to draw it out. That's our universe, and so I said A, said B. I'm sorry, I can't draw good circles. Anyways, the intersection is a part in the center. Let's fill that in, 325. So for part A of the problem, we need to find the cardinal number of the union. And thankfully, we kind of already learned a formula about that 2 slides ago. So let's directly apply it. We just substitute everything in sort of, and you do the math. And 525, yep. And then for the second part, we use the idea that like the number of A, the cardinal number of A union B complement is kind of the universe minus the cardinal number of A union B. Yep, and again we can substitute our information. And yep, let's fill that in. For the third part, we kind of want the everything which is in A but not in B, so we can use the information we already have or which we've already calculated. Again, substitute and fill it in. And that would be this part right over here. Yeah, and finally the B minus A part, you could calculate it if you wanted, though the problem doesn't really ask that from us. And these kinds of problems, the first formula is something we explicitly used, but the second and third, we're kind of using logic here, we're manipulating the problem, so it would be good to practice these and get a good conceptual understanding so you don't have to memorize completely random formulae. Practice is your friend, and practice is till it feels kind of comfortable and instinctive. Okay, here's one more problem. This one is kind of big, but when these kinds of questions do come in the boards, they come for a lot of marks, so it's definitely worth trying out. Pause for a minute to try it out. Okay, so that's a lot of words right there. Let's sort of assign everything a letter first, which we're going to do in our Venn diagram. Okay, F is French, G is German, R is Russian, and let's write everything in the language of sets, if you would. So here's all the information they're giving us. F union G union R is people taking at least one language, and that's 100. And the total number of students is 120. So that's our universe. If you think about it, intersection is kind of like and union's kind of like or, so which is kind of translating that into sets from English. And yeah, this is what we're supposed to find. So just give me a minute. I'm going to move that into a new slide so we have more space. Okay, so here we are. This is the information we already have. And to find this part, the part we need to find, the number of the intersection of all three, we can use our neat little formula from before. Again, it might take a while to remember this one. You don't have to actively memorize, but with practice, you're going to get it. Yeah. And this last little bit here is what we want to find. So I'm going to call that X. And we basically are given the rest of the information. So we can just substitute. So we're just substituting everything we already know or have been given. And okay, can cancel some stuff out here. Yep, and X is 8. So that is our answer. There are 8 people studying all 3 languages. So let's put it in the Venn diagram. I mean, we don't really have to, but I'm going to tell you why we're doing it in a few seconds. So that's our universe. Yeah, and that little part in there is 8. So I've moved everything into the slide, and luckily for us, that was all this problem asked from us, but most likely you're going to get asked more stuff, or there'll be more subparts to the question. For example, they might ask you how many students are studying only French and no other language, for example, or how many are studying German and Russian but not French. For that, we kind of want to fill in all the little parts of the Venn diagram to be able to answer, and it is important to understand what each part represents. So let's find what goes in all of these pieces. Yep, so I want to find what happens in like this little part. There's a difference of the part in green and yellow. No, give me a minute. So yeah, I'm going to call that part A, which I want to find, and I'll label everything else. So using what we've already been given and what we calculated, we can find stuff. So I'll do a few for you. As we said, we want to find part A, and that these are the parts we need to use. F intersection R, and the intersection of all 3, and we can substitute. minus 25, and 8. And we get A is 17. 17, yeah. Let's fill that in the drawing as well. And if you want to find C, we take the intersection of F and G and subtract again the intersection of all three. So that would be 20. Minus 8, and we get C is 12. The yellow stuff at the top is what we were given, and we are using that. So similarly, we can calculate all the other parts. So give it a shot and come back in a minute. So the final diagram will look like this. Now you can easily look at it and answer any other questions you are asked. People who study French and nothing else, 28. And people who don't take a language, that's everything outside F, G, and R, which is 20. So for these kinds of questions, I would like to give you some tips. First is to read the question carefully. It has all the information you need. Underline stuff if you need to, and then draw a diagram to make it all make sense. Put in what we already know if possible, and fill in all the parts like we did. And finally, everything adds up. So for example, they said 65 people took French rate in the original problem. So look at the circle F, and if we add up all the parts, give me a minute. This parts 45, 20, yeah, that's 65. Similarly, check everything else to catch any mistakes before you submit your work. Here's a recap of everything we did today. I would ask you to remember De Morgan's laws and maybe those two formulae of the cardinal numbers that we used in our last two practice problems. Practice the word problems, the shading Venn diagram problems, and please don't neglect the rest of the theory because it might come in short answer questions. Past year questions are a good way to practice, especially prioritize the more recent ones because the pattern of the paper has changed recently. And before we go, I would like to say that while I think I covered everything, do check your syllabus and your textbook for anything I may have missed. Thank you so much for staying with me this far. I hope you found this video useful. Stay tuned for more of these. Bye!